A Combinatorial Introduction to Topology by Michael Henley. Chapter 1, Basic Concepts. Section 1, The Combinatorial Method. Topology is a branch of geometry. To get an idea of its subject matter, imagine a geometric figure, such as a circular disc cut from a sheet of rubber and subjected to all sorts of twisting, pulling, and stretching. Any deformation of this sort is permitted, provided the rubber can withstand it without ripping or tearing. Figure 1.1 shows some of the shapes the disc might assume. The rubber must be very flexible. Perhaps silly putty would work. Technically, these distortions are called continuous transformations. The formal definition of topology is the study of properties of figures that endure when the figures are subjected to continuous transformations. Technical details will come later, Section 2. In this section, we wish to describe some of the ideas of topology at the intuitive level, where topology has earned the nickname rubber sheet geometry. From Figure 1.1, it is clear that a continuous transformation can destroy all the usual geometric properties of the disk, such as its shape, area, and perimeter. Therefore, these are not topological properties of the disk. Any topological properties the disk has must be shared with the other shapes in Figure 1.1. These shapes are called topologically equivalent, meaning that any one of them can be continuously transformed into any other. Although topology will seem very different from Euclidean geometry, the two are fundamentally alike. In Euclidean geometry, there is also a basic group of transformations called congruences. The subject matter of Euclidean geometry is determined by the congruences, just as the subject matter of topology is determined by the continuous transformations. The congruences all preserve distances. For this reason, they are also called rigid motions. Under a rigid motion, a disk remains a circular disk with the same shape, radius, area, and perimeter. Therefore, these are Euclidean properties of the disk. Euclidean geometry can be defined as the study of those properties of figures that endure when the figures are subjected to rigid motions. What is a topological property of the disk? For one thing, the disk is in one piece. This is a topological property, since any attempt to divide the disk into more than one piece would require cutting or tearing, and these are forbidden in continuous transformations. Another topological property of the disk is that it has just one boundary curve. Another plane figure of some importance in topology, the annulus or ring shape, see Figure 1.2, can be distinguished from the disk by this property, since the annulus has two boundary curves. Another property distinguishes the disk from the annulus is that the latter divides the plane into two parts, while the former does not. Exercises. 1. Examine some familiar objects topologically. For example, which of the following objects are topologically equivalent? Hand iron, baseball bat, pretzel, telephone handset, rubber band, chair, consider several types, funnel, a scissor, frisbee, etc. 2. Why is it said that a topologist is someone who can't tell a donut from a coffee cup? Let us call any figure topologically equivalent to a disk a cell. A cell is one of the simplest topological figures. The first principle of combinatorial topology is to study the complicated figures that can be built in some way from simple figures. To put this principle into practice in this book, we will restrict ourselves to figures that can be constructed from cells by gluing and pasting them together along their edges. Figure 1.3 gives some examples. The edges of the cells sewn together to make each example are clearly marked. The number of cells used are 4, 7, 8, 8, 3, and 5, respectively. These numbers are not rigidly determined. For example, it would be simpler to build a sphere from just two cells, like the northern and southern hemispheres of a globe, or the two hourglass-shaped cells that are sewn together to make a baseball, Figure 1.4. Figures like these are called complexes. All but the most pathological of geometric surfaces are complexes. That is, they can be regarded as built in this way from cells. Exercises. 3. Examine the surface presented by some familiar objects. In each case, try to show how the surface can be constructed from cells. 4. Adopt the rule that no cell is to be sewn to itself. Find the minimum number of cells needed to make an annulus, a double annulus, and so forth. Do these numbers change if the cells are permitted to be sewn to themselves? The combinatorial method is used not only to construct complicated figures from simple ones, but also to deduce properties of the complicated from the simple. This idea is actually common to much of mathematics. In combinatorial topology, it is remarkable that the only machinery needed to make these deductions is the elementary process of counting. This is the miracle of combinatorial topology, that counting alone suffices to found a sophisticated geometric theory. This reliance on counting is what distinguishes combinatorial topology from other branches of topology and geometry. In order to count, we must have something to count. To this end, we jazz up cells a bit. We call a cell a polygon when a finite number of points on the boundary are chosen as vertices. The sections of boundary in between the vertices are then called edges. A polygon is called an n-gon, where n is the number of vertices. The complexes in Figure 1.3 are actually built from cells in the form of polygons. Thus, the annulus there is composed of 4 fourgons, while the double annulus is composed of 3 fourgons and 4 fivegons. As a further example, Figure 1.5 shows a set of 4 three-gons, a fourgon, and a fivegon that have often been successfully sold commercially as a puzzle. The same figure shows 2 complexes among many that can be made from these polygons, a rectangle and a letter T. Of course, considered topologically, these 2 complexes are equivalent. In fact, after the pieces of the puzzle are sewn together, both complexes are cells. The choice of certain points as vertices in order to be able to regard cells as polygons may seem irrelevant to topology. However, it provides something to count, and so affords the combinatorial method something with which to work. In the future, we assume that all complexes are formed from polygons, and further, we adopt the rule that vertices are sewn to vertices and whole edges are sewn to whole edges. As an application of the combinatorial method, here is a derivation of a famous result, Euler's formula for polyhedra. A polyhedron is a complex that is topologically equivalent to a sphere. For example, the sphere in Figure 1.3 is a polyhedron, an octahedron in this terminology. Given a polyhedron, let F stand for the number of cells, called faces in this context, E the number of edges, and V the number of vertices. Euler's formula states that F minus E plus V equals 2, equation 1. This remarkable result is the earliest discovery in combinatorial topology. It is due to Descartes, 1639, but bears the name of Euler, who rediscovered it and published a proof in 1751. The following proof is due to Cauchy, 1811. We begin by removing one of the faces of the polyhedron. The remainder is topologically equivalent to a cell and so may be flattened into a plane. For example, Figure 1.6 shows this operation being performed on a cube. The result is a cell in the plane divided into polygons. By removing one face and leaving edges and vertices intact, the sum F minus E plus V has been decreased by 1. We must now prove in general for a complex equivalent to a cell that F minus E plus V equals 1. Equation 2. This is called Euler's formula for a cell. It applies, for example, to the 2 complexes of Figure 1.5. The next step is to triangulate the complex. Divide each polygon into triangles by drawing diagonals, as in Figure 1.7. Each diagonal adds one edge and one face to the complex, so that the quantity F minus E plus V is unchanged by this process. In the final step, the triangles of the figure are removed one by one, starting with those on the boundary. There are 2 types of removal depending on whether the triangle being removed has 1 or 2 edges on the boundary. Figure 1.8. In the first case, the removal decreases both f and e by 1, while in the second case, f and e decrease by 1 and e decreases by 2. In any event, the quantity f minus e plus v is unchanged by the removal. Eventually, we are left with just one triangle for which f equals 1, e equals 3, and v equals 3. Obviously here, f minus e plus v is equal to 1. Since steps 2 and 3 did not alter the sum f minus e plus v, this proves Euler's formula. Exercises. 5. Repeat exercise 4, assuming this time that all cells are in the form of polygons, and supposing that no cell can be sewn to itself or to any other cell along more than one edge. 6. Confirm Euler's formula for polyhedra in the case of the cube and octahedron. Confirm Euler's formula for cells for the complexes in Figure 1.5. 7. Carry out the steps of the proof of Euler's formula for a tetrahedron, triangular pyramid, and an octahedron. To appreciate the topological value of Euler's formula, consider it for a moment from the point of view of the sphere. Euler's formula says that no matter how the sphere may be subdivided into polygons, the sum of the number of faces minus the number of edges plus the number of vertices is 2, always. Rather, like the surface area of the sphere, the number 2 is a property of the sphere itself. For although it is discovered only by dividing the sphere into polygons and then counting and adding faces, edges, and vertices, the number 2 is independent of the manner of this division. Unlike surface area, however, the number 2 is also a topological property of the sphere, since the proof of Euler's formula is valid for any figure topologically equivalent to the sphere. Thus, a topological property can result from the introduction of the seemingly irrelevant vertices and edges. This is the whole point of the combinatorial method. Although its meaning is not completely clear yet, in fact, the number 2 is the single most important topological property of the sphere. The remainder of this book may be regarded as an elaborate justification of this assertion. The number 2 is called the Euler characteristic of the sphere. Similarly, on account of equation 2, the Euler characteristic of the cell is 1. As an application of Euler's formula, we can determine all the regular polyhedra. A regular polyhedron is one in which all faces have the same number of edges and the same number of faces meet at each vertex. The cube is an example of a regular polyhedron. All faces have 4 edges and all vertices lie on 3 faces. The Greeks discovered 5 regular polyhedra. They are called Platonic solids, and their construction is the climax of Euclid's Elements. We shall soon see why there are no others. Let A be the number of edges on each face of a regular polyhedron, and let B be the number of edges meeting at each vertex. Then the number AF counts all the edges face by face. Each edge is counted twice in this way, since each edge belongs to 2 faces. In other words, AF equals 2E. Similarly, since each edge has 2 vertices, BV equals 2E. Euler's formula now reads 2E divided by A minus E plus 2E divided by B equals 2, or 1 over A plus 1 over B minus 1 over 2 equals 1 over E, equation 3. This is an example of a Diophantine equation, so called because the solutions A, B, and E, by the nature of the problem, must be positive integers, and because equations with solutions of this type were studied by the Greek mathematician Diophantus. The restriction of the positive integers is an immense simplification. In this case, it makes a complete solution possible. Actually, both A and B must be greater than 2, since faces or vertices with only one edge are impossible, and those with just 2 edges are usually deliberately excluded. Since both A and B are greater than 2, they must also be less than 6 in order that the left-hand side of 3 be positive. Thus, when A and B are greater than 2, there are only a finite number of possibilities, and the solutions may be found by trial and error. There turn out to be just 5 solutions, each corresponding to a polyhedron that can actually be constructed using Euclidean polygons. The solutions are illustrated in Figure 1.9. Exercises 8. Given a polyhedron, not necessarily regular, let f sub n be the number of n-gon faces, and let v sub n be the number of vertices at which exactly n edges meet. Verify the following equations. A. F sub 3 plus f sub 4 plus f sub 5 plus ... equals f. B. V sub 3 plus V sub 4 plus V sub 5 plus ... equals V. C. 3 f sub 3 plus 4 f sub 4 plus 5 f sub 5 plus ... equals 2e. D. 3 v sub 3 plus 4 v sub 4 plus 5 v sub 5 plus ... equals 2e. E. 2 v sub 3 plus 2 v sub 4 plus 2 v sub 5 plus ... minus the quantity f sub 3 plus 2 f sub 4 plus 3 f sub 5 plus ... equals 4. The quantity 2f sub 3 plus 2f sub 4 plus 2f sub 5 plus ... minus the quantity v sub 3 plus 2v sub 4 plus 3v sub 5 plus ... equals 4. 9. Using E and F of the preceding exercise, show that the quantity f sub 3 minus f sub 5 minus 2f sub 6 minus 3f sub 7 minus ... plus v sub 3 minus v sub 5 minus 2v sub 6 minus 3v sub 7 minus ... equals 8. Conclude that every polyhedron must have either triangular faces or trivalent vertices. Similarly, by eliminating f sub 6 between E and F, deduce that the quantity 3f sub 3 plus 2f sub 4 plus f sub 5 minus f sub 7 minus 2f sub 8 minus ... minus the quantity 2v sub 4 plus 4v sub 5 plus 6v sub 6 plus 8v sub 7 plus ... equals 12. Therefore, every polyhedron must have triangles, fourgons, or fivegons. Show that if a polyhedron has no triangles or fourgons, then it must have at least 12 fivegons. Is there a polyhedron with this minimal number of fivegons? 10. F and V play symmetrical roles in Euler's formula. Let two polyhedra be called dual if the number of faces of one is the number of vertices of the other, and vice versa. Find the duals of the Platonic solids. 11. Find the solutions of equation 3 when A or B are allowed to equal 2. The corresponding polyhedra are called degenerate. Draw them. 12. Show that the Euler characteristic of the annulus is 0. Investigate the characteristic of the double annulus, torus, and so forth. 13. Little is known of the life of Delphantus, but the following problem from a Greek collection supplies some information. His boyhood lasted 1/6 of his life. His beard grew after 1/12 more. He married after 1/7 more, and his son was born 5 years later. The son lived 1/2 as long as the father, and the father died 4 years after the son. How long did Delphantus live? Analytic Conics by Barry Spain, Trinity College, Dublin, May. Published by Pergamon Press, London, 1957. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.